that? This is, let's say, the bare minimum that we're hoping we need to be able to solve um, a large set of problems, but not all of the problems. So I'm moving into the Go training topics, Go generics section of the repo. There's a README here. You'll see a link right here for the draft proposal. You'll see a link right here for the Go playground. This will allow you to play at home, or you can also install it on your machine. I'm going to show you that in a second. I've left the high level overview of what this current draft is going to be supporting for generics. Again, it's not necessarily the final list. Some of this might come out. Some of this still might be added to. It's just a first release trying to solve some very specific problems that seem to be the larger problems that we have today, not having generics. And I'm going to show you code for that. Here are the emissions as they are of today. This list could change by the time we have a release. And I'm not going to go through it. It's there for you to read there in the draft. And I've already installed this version of Go locally. And these instructions here will show you how to do that. And these are the instructions that I followed on my machine. And there hasn't really been an update to the code since the 9th. And we're going to be running that. And you're going to see me doing this Go run generic. And if I switch over, you'll see that I'm running a version that I built around July 9th. I haven't really seen any changes to this as well. So I'm running against the current source code and the Go dev branch like you see here. Okay, this talk does assume at some level you've written code in Go before. If you haven't, it's okay. I will go through some of this fairly slowly in the beginning. If the font size isn't large enough, let's see. I'll go one level bigger. Let me know, but I'm going to start from here. Now, I want to spend an hour, that's just about in an hour. This hour is going to go by really fast. Trying to show you the draft, right? Not going after the things that aren't there, but the things that are. So we're definitely going to go through 1, 2, 3, 4, 5, and 6. That is my goal. If we still have time after 6, I'll try to show you a little bit on number 10. But the rest of this will be for you to look at and then experiment. And I've commented this out as well as I can. Okay, with all that being said, let's jump into it. Now, I want to start with the basic syntax for generics and then share with you why the syntax also is what it is. And then we'll continue to add aspects of programs that you're writing today and how generics could help. So let's take a look at these two functions right here. These are the print functions. One can print a collection or a slice of integers. One can print a slice of strings. And if I wanted to print a slice of floats, well, I'd have to write another function that can take a slice of that specific concrete type, float64, and write it. But if you look at the code I had to write, I think we can argue that it's fairly consumable by many of us, especially if we've spent a couple of months already writing Go. I've got a basic fump print statement. I'm doing a linear traversal using the for range. The code really looks the same across both of these concrete print functions. And we're looking at really, 5 lines of code at the end of the day. But if I want to work with a slice of floats, I would have to copy and paste these lines of code. And really the only thing that would change, because fumped technically is a generic function thanks to reflection, would be the parameter. Now, in the current version of Go, I could begin to write a generic function. I could use the empty interface. And I could write a function like this, print interface. And the print interface function uses the empty interface to accept a slice of any type. I could pass a slice of int, a slice of string, and a slice of float. However, in this particular case, I'm using type assertions as a way of writing generics. Now that kind of limits me because now I'm still bound to writing the different versions of handling different types. I've essentially, if we look at this code, have moved away from writing functions to just writing case statements, but it does give me a single function that could accept a slice of any type as long as I code a slice of that type. I should have a default case here at some point for the code I didn't implement. But we're getting closer to writing generics in Go. Now, I could write a fully generic function in Go today. Let's not kid ourselves. I can if I use reflection. This is technically a fully generic function. I'm missing a little bit of error handling here, but you can see here that I can still accept a slice of any type using the empty interface. I can validate using reflection code that that slice or the data stored inside the empty interface is a slice. If it's not, I got a little error handling here to do, which I haven't done here. That's fair, but I can do it. And then I can perform a linear traversal. And again, thanks to func being already generic through reflection, I can handle a slice of any type, and I've coded it once. Now, there's a lot more code here than what we've seen, and maybe takes a little bit more effort to understand it and to write it, but it's here. So our reflection package is allowing us today to write generic functions. But how does generics, or at least the current draft of generics, maybe allow us to write a function that is, again, could handle a slice of any type without all the complexity maybe of reflection? Here it is. Here is a generic version of this print function. Now, I'm going to do something initially here so we can break down the syntax of this function and better understand it. I'm just going to remove those parentheses for 1 second. And I want you to notice that the implementation of this function is really identical to the implementation of our initial concrete functions that we had, the 1, 2, 3, 4, 5 lines of code. And so it's almost like we're able to write the concrete function as if we were working with one type, but then take that implementation and we want to find a way of allowing it to work with any type. Now, if you look at the function signature as is right now, you see me use a capital T to denote the type of slice. Ideally, what I'm trying to do and what I want to tell the compiler is, hey, compiler, I would like this function to accept a slice of type T, where type T is not going to be defined by me, but I need you to identify what T is at the call site. You see, this syntax, the way it is right now, assumes that I'm going to come in and define a type of T to satisfy the compiler's understanding of what this type is. But in a generic function, the idea is that the declaration of T in this case is not on me, it's not on you, it's on the compiler to identify. And so there has to be a way in syntax to tell the compiler that T is not going to be defined by me, it has to be defined by you. And so going through all the different iterations over the last 10 years, what we've come up with at this point is another set of parentheses that we're going to call a type parameter list. And this type list is a way of telling the compiler, hey, T is going to be a type, but not declared by me, a type to be identified by you. And so now we have a syntax here using a type list, our parentheses around a type list, parentheses around our data input. And now we're able to tell the compiler, hey, T, I want to accept a slice of T defined by you. Okay, great. So here we are. And it's this parenthesis list that I first really want you to look at and study and understand. And part of the talk here, as I share syntax, is for you to continue to ask yourself, does this look and feel like Go? Does this look and feel like Go? And as I explain some syntax choices, maybe that will help you start to realize it. So again, anytime we see this type and some identifier, what we're going to try to say to the compiler is, I'm not going to be defining T in this case. I'm going to be asking you to define T. And I like using these single capital letters myself. This is an identifier. It can be anything you want it to be. The point is that we want the code to be readable. And so we want to make sure that when we're reading the code, it's obvious what these things that we're naming are, right? It's a big part of what we do in Go. So when a value can be anything of some type, you're going to see me using these single character letters because we don't do this in Go. And I think it's a nice readability marker to show that this is going to be a generic type to be determined by the compile time at the call site or at the construction site. Okay, great. Now let's just see this code run in action. So I can construct a slice of integers and during construction initialize it. I can construct a slice of strings and during construction initialize it. And you can see my 4 print functions work with that data. Now I'm going to come into the terminal. Where are we here? Good. We'll make it a little bit bigger. We'll come into the basic. And since I've installed the Go here, I'm going to use my Go tooling. I'm going to use the run command and feed it the, notice the go-to file. And what this go command does is it's a transpiler. So it's going to take the code inside the go-to file, convert it into a .go file, which is proper Go code the compiler can build and run. And so it's a transpiler for the draft syntax for generics. And you can see here that the output is the same in every version of this code that we have. Now, if I wanted to work with a slice of floats, right? Float 64. There we are. We know right now that the only 2 functions that we'll work with are our true generic functions, right? We know that print reflect is a true generic function because of reflection, but this is the cool part here. The cool part here is that the compiler can basically write for us a print generic version based on the data that we pass in this case, float. And so if I've done everything right here, we now see with no more programming really, that we have a generic version of that code that can work with floats. Now, if we come back to this syntax, this is a parameter list. It's a parameter list of types where T is to be determined, in this case, at the call site. So I want you to know that we could, in a longhand, specify that type information to the compiler. In this particular case, we're telling the compiler, don't worry about trying to infer the type. I'm telling you what it is. But what's nice and what we're going after as much as we can is the compiler inferring the type. In this case, the compiler can do the inference because it sees that we're passing a slice of float. You can see that float is the base type here, right? It's the underlying type. And it can substitute float for T and validate that the float works. And so I think it's important that as we continue to work and play with the generics, that we find ways for the compiler to be able to infer the type. There may be times when the compiler can't. And I would argue right now, today, July 14th, from the little experience that I have, that if the compiler can't infer the type, maybe we're doing something that isn't exactly right, or maybe we're doing something a little more complex than we need to. In every case where I thought the compiler couldn't infer the type, I sent the code to the language team, and they gave me back a solution where the compiler could. So I want to look for that solution as well. Now, again, we're still learning, but I'm trying to identify some sort of code smells and areas where maybe we're not using generics 100% correctly, or maybe we shouldn't be using them at all. So here we are. We've got our first generic function where we now see the syntax of this type list as a parameter list of types to be determined at compile time, in this case, at the call site. Okay, I'm going to stop real quick here. If anybody has any, I don't want opinions just yet, but questions on what we have right here, I will take a couple of them now. If not, we're going to continue to move on. Okay, I don't see anything. Again, I can't see the chat window, so I'm going to need help from the organizers to just raise a hand when I ask. All right, let's move on. All right. Now, that's good and all, but we have a programming language that lets us define the structure of data. And we have to be able to do that. We've got to be able to have user-defined types if we're going to solve any real-world problems. So let's take a look at some code here related to user-defined types. Now on line 11, I'm defining a user-defined type named vector int. On line 18, vector string. And you can see again the underlying type of these name types are collections, a slice of int and a slice of string. But because this is a named type, it's a user-defined type, I can apply behavior to these types. Here I've added a push method and a push method. Now, this particular push method is bound to the underlying type of int, and that's what we can push in our vector. This push method is bound to the underlying type of string, and we can append it to our vector here. Now, understand something. Even beyond reflection, Go technically has generics already. Go has a set of built-in functions, like append, like make, like copy, which are in essence generic functions. Append, in this case, can take a slice of any type and a value of any type, and as long as they're compatible, can perform that appending operation. The problem is that the way the language team has been able to write functions like append and make and copy has not been extended to us, right? And so we don't get to be able to write these same types of functions. A lot of it has to do with being able to kind of controlling the compiler, so it's not extended to us. But I just want you to understand that at least in these examples, I'm leveraging right now the fact that append is a generic function in and of itself. But here we are. I've got these concrete types that I've defined, again, with underlying collections. And the underlying type is part of the parameter list for the method. Now, I could, again, write this in a much more generic way by leveraging the empty interface. Now I have a slice of the empty interface. Again, I can accept a value of any type, and append works perfectly, exactly the same way with really no extra complexity because of the nature of append. But this does have maybe a downturn, because this vector interface type will accept a value of any type. It is not restricted to just one type like these are. Maybe that's good. I don't know, maybe that's bad, because we could be mixing different data types in this with no real way to restrict that. So what does a generics version of this code look like? Okay. Now, remember, at least in these early examples, when you see T, I want to tell the compiler that T is not going to be defined by me, but to be defined by you, in this case at the construction site, to be defined by you at the call site. And so we need our type parameter list again. This syntax now being applied against the type name tells the compiler that T will be determined by you, or at least I will specify what T is going to be at the construction site. Now, when we define this method, we have to continue to tell the compiler that this method is bound to a vector generic of some type T to be determined at compile time. So you're seeing that parentheses again. We've got our push method, again, of some type T, and the return is a vector generic of some type T. And again, we're lucky because I'm sorry about that, somebody's walking by talking loud. And on line 49, we have our generic append function that works just as it is. But I want you to see how we're applying the generic type T list to the type declaration here. Now, let's get a sense of how this code works. I've got my vector int and I've got my vector string. We're able to use the push methods that are bound to the same underlying type. We see that. We have our vector interface. And as I said to you, I think one of the downfalls of using the empty interface on our vector is that this can now use a collection of any different types. We're not restricted. We're not bound to a single int or a string. We can do that. But our generic syntax gets us back to this without having to write another version for different types. And so here you can see on the construction of a vector generic, we're going to use that type list, that parameterized type list, to specify to the compiler what type or what should be underlying type be to the vector. Now we have to specify the type information here. There's no way to infer it. When we're calling a function, the compiler can find ways to infer the type. But when we're constructing a type, now we're going to have to pass that type information in. And now that push will be bound to type T. In this particular case, the compiler can infer T because it knows that this variable, the receiver, is already bound to the underlying type. It can identify that push here has to accept a string because it can infer it based on the receiver. Pretty cool. And I can run this code again. Here we're on number 2. We can run it. We can see that our vector interface works with both int and strings, and technically will work with almost any type. And then we have our generic versions that are bound to the underlying type that we specify. And again, this is generic technically, but we're not restricting the information here. This should work. I could pass floats without any extra code. And once again, I don't have to write a float 64 version. We can do that. We can do this. I can make sure that we use the right float variable. And once again, we can now start passing floats. And there we are, it's all really nice. So we're now seeing an example of where we're defining a name type, which will have some aspect of a generic type, in this case, a collection of some type T to be determined at compile time. And that determined at compile time is now happening during construction. And here we're passing the type information in. And so this set of parentheses is being represented here at the construction site. And it's a case where we do now have to specify the type information, but we don't have to do this. We don't have to do this because the compiler can infer the type based on the fact that it already knows the receiver is using the underlying int in this case. Nice. Okay. Again, any questions, not comments just yet, but questions on this particular piece of code? Excellent.
There are quick questions.
Yeah.
So one from Thapakazi, that is there any cost of type inferal behind the scene?
No cost because it's all happening at compile time. If anything, the compiler maybe gets slower, but they're going to work really, really hard in keeping the compiler performance. And because compiler performance is so important in Go, it's also restricting some of the things we can and can't do. And so at this point, no, the only cost would be maybe the compiler has a little more work to do.
Second question is by Bhaskar. Would you like to ask it? Okay.
So, so the letter T, that will be some kind of a container defined by the compiler that would hold type information dynamically at the runtime.
So you're asking, will reflection work against these generic types? I believe it will. I have to double check the spec. But one thing, I'm going to say yes right now, but we got to double check the spec. And I'm going to say yes because the language team is really focused on making sure that there's backwards compatibility with everything and things don't break. But I haven't, you're the first one, honestly, to ask that question. And I remember hearing some rumblings about it. Okay. We do not propose to change the reflect package in any way. When a type or function is instantiated, all the type parameters will become ordinary generic types. Yes. So there's your answer right there. I mean, what the compiler's doing essentially is generating code for you or a version of that, say, function that accepts a value of that particular type. So as I suspected, and as it's there for here, the reflection package is going to be fully supported as it is today.
Right.
Great question.
Thank you. Thank you.
Okay. So let's continue on. So I've defined this generic type in a sense, right? Or at least a type that can be bound to some generic type information. And so far, the method push works with any value of type T. But what if I'm implementing a method here where certain criteria has to be met? In other words, we can't just pass any value of type T because we can't assume that every value of type T can behave in a certain way. In other words, what we need in the spec is a way of defining a constraint against the data. So we can guarantee a compile time that maybe in one case certain behavior exists. Because if not, then at runtime, we're going to blow up. So let's take a look at how we can define constraint, specifically behavioral constraint, with our generic, in this case, functions. So to start off, I'm defining two user-defined types, one named user, one named customer. We're using our struct syntax. And you can see here that in both cases, for user and customer, I've defined a method named string that returns a string. Now, for some of you who have worked in Go long enough, you may have noticed that these methods conform to an interface that we call the stringer interface that can be found in both the fumped and the log packages. Essentially, I'm using these methods so I am compliant with the stringer interface. Now, once again, like you've seen so far, I can define functions that could stringify a user or stringify a customer. And the idea is that we take a collection of users and write a collection of that in a string version, maybe JSON. Or I can take that collection of customers and convert it into a slice of strings, maybe in JSON. But once again, because a slice of user and a slice of customer is different, I have to write an individual implementation. But the implementation, again, is only 5 lines of code, and we can all consume that. We can all read it with enough time and Go. We can really understand that almost like this. How do we write a generic version of our stringify functions? Well, we're back to the idea of using the empty interface and case statements. But again, if we're using type assertions and case statements, well, it's not fully generic. It's only for those implementations that we've done. We saw that before. I can write a fully generic version of stringify using reflection. Again, this will work. We go into our reflect call. We validate that it's a slice. Again, we're not really handling errors properly or mismatches there. That's okay. We can do our linear traversal. I can even make a call to string. Remember, these functions are calling the string method to do the stringify. The string method is critical here. We know that string works off of a underlying type user. We know that at the compiler point. We know that. We knew it here as well. But here I'm doing it through reflection. Now, you might notice that I'm not validating that the method string exists. I do have more work here if I really want to make sure that we don't have some sort of panic at runtime. But I did want to show you that using reflection, we can make method calls at runtime against data when that method call exists. There we are. And again, fully generic version, a little bit more code, a little bit more complexity, but it will work. But what about generics here? Now, here is our generic function. And again, remember the same basic 4 lines of code that we wrote for either the slice of int or the slice of string are represented here. And again, we're getting benefits from the append function. Once again, my parameter list of input says that I will accept a slice of some type t, and this is telling the compiler of some type t to be determined at compile time on the call site. However, because we are expecting a method named string to be associated with a value of type t, the underlying type, we have to tell the compiler that the data must be constrained here. We must guarantee, compiler, that whatever value of type t exists, it has a string method. Now, what we're going to do is leverage interfaces. And when you think about it, the interface is really perfect here. An interface already defines a constraint against behavior, right? I could write a polymorphic function that says, I will accept a value of any type of data as long as it implements, in this case, let's do it like this, right? We already use interfaces to define a constraint on behavior. This function on line 107 already says, I will accept any value or pointer that implements the stringer interface, that complies, that has a string method that returns a string. We're already using interfaces in this particular case. What we're now going to do is use the interface to apply that same sort of behavioral constraint, but we're going to apply it to what t is allowed to be. And in this case, we're going to say that the underlying type of this collection, type t, must have a method named string. Pretty cool. And so we're applying it to the type list. Now, because of that constraint, look at what we're going to do. I can construct a slice of users, pass them through all 4 of our functions. I can pass the slice of customer, pass it all through. We know, again, that the compiler can look at the underlying type of our collection user, and the compiler can infer user here. We don't have to pass it along. Beautiful. We also know the following. Let's build this first and run it. All of it works. We have a JSON-like pretty print version of our user and customer types. Now, what else do we know? Well, we know that I could construct a slice of floats. I'm not going to do it. And we could pass it to these 2 functions. We know that. But what I want to show you is what happens if I remove the constraint. What if I don't constrain t in this particular case? Look at what the compiler does. The compiler is getting really good at providing good error information. In this case, look what the compiler says. Hey, Bill, on line 110, you've defined that value will have a method named string, but you haven't defined the constraint here for t to have it. So I'm sorry, but this doesn't work. In other words, the compiler's identified that you want the string behavior to exist on the underlying type, but you haven't made that very clear. So it's really important when we have an implementation that's going to require behavioral constraints that we define what those constraints are, so the compiler can guarantee that we don't pass some value of some type that doesn't conform to the constraint, in this case, the behavioral constraint. Okay, any questions here? Not comments just yet, just questions. Good. All right, now, constraint is important. And thanks to the interface, we have the ability to leverage the goodness of that interface in terms of applying behavioral constraints. But that being said, there are times where the constraint that we need to apply is not behavioral as much as it is, I would say, a property of the data. What if we wanted to apply arithmetic to our implementation? What if we wanted to add two things together? Well, not all data has the ability to be added. Your struct types don't have the ability to be used in a plus operation. And we don't have the concepts of operator overloading in Go. So it's not like we can even conform the data to certain operations. So let's take a look at how the current syntax or draft proposal handles these types of maybe property-based constraints, is what I'm calling them. I really want you to start on line 18 with our generic function add. Again, we know it's a generic function because it has a parameter type list of type T, where we're saying the first parameter will be of type T, the second parameter will be of type T, and we're going to add those two parameters together and return the sum of T. Again, the problem is not all types in the system will support the plus operator. So what do? Well, we have to add a constraint so only data that can be used in a plus operation can be applied. The current draft implementation says what we'll do, leveraging the interface, since interfaces can be applied as constraints today in the type list, is to add a type list inside the interface itself. And so what you're seeing me doing in the add-only interface is saying clearly to the compiler, the only data that will conform to this interface, the only data that, or the data that we're going to constrain ourselves to, is in this list. Ints of any precision, the float 64, and the string. And you can see here that we're now saying that this is the only data that we support in terms of being able to be passed into add. Okay, so we can now apply a type list to the add-only interface. Now, your question is going to be, well, Bill, when we do that, can we apply it to our traditional polymorphic functions? Can I do this? And the answer is no. Right now in the current draft design, if you write an interface that contains a type list, then it can't be used as a polymorphic function in the traditional sense. Now, I will tell you that the language team isn't happy with this. This isn't something that we do in Go. The classic example already was, hey, we're going to support reflection because we expect that reflection should work. Just because it's a generic type, that doesn't mean that should break. And so one could argue that this is really helping in terms of being able to apply property constraint. But the fact that it's breaking some Go code today in terms of now we can't use this interface in a polymorphic way, you know, like this, hurts. So the language team is looking at different ways we can apply this kind of type list to these generic functions without breaking the interface. So if you have ideas around this, they are all ears. Now, that being said, let's say by August, we flush a lot of things out, and this is still the leading #1 contender for applying this type of constraint. It's quite possible that this still gets in, And it's quite possible that we won't be able to write functions that support it. Maybe what they end up doing, however, is finding a way of allowing us to write polymorphic functions that do support it. I don't know. I'm just sharing this with you because you might be looking at this going, Bill, this is the first time I'm looking at code that doesn't make me feel all warm and fuzzy about Go. Well, you're not alone. The language team also isn't feeling warm and fuzzy here. Now, personally, and we can talk about this when I ask you for your opinions. I want to hear it. But personally, I don't have a problem with this. I kind of like it where it is. It simplifies things. And again, I don't have a problem not being able to do that if it keeps things simple. Though you may not necessarily know that until you get the compiler error. Anyway, you can chew all of that in your head. It's something that we can talk about. But we do need the ability to provide this type of constraint. And this is where it is today. Let me continue on here. I want you to notice that I'm defining user-defined types again. In this case, I have an underlying type of int64 and string. I've implemented behavior. It's match behavior, nothing over the top. I've also defined a struct type named Bill with one field called name, and I've implemented match for Bill as well. Bill matches bills, and fruit matches fruits, and duration matches durations. Now, what if I wanted to write a generic function named match that took a collection of some type T and a value of some type T and used the match behavior that should exist for this value of type T and range over the collection trying to match V in this case to any value in the collection. Essentially, given a collection and given a value to find, see if it exists in any item in the collection itself. So once again, this is going to be a generic function, and T is going to be determined at compile time, and T in this case now is constrained to this interface. Now I want you to look at this interface because we're defining this interface also as a generic type. We're going to have something of type T to be determined at compile time. In this case, it is the parameter to the match method that all values of type T in this function have to be able to conform to. I'm showing you this because I'm defining an interface that defines behavioral constraint and defines property constraint. And I want you to notice that I'm able to pass my struct type as a property constraint. I'm able to use fruit as a property constraint. Okay? And again, the compiler can infer these types on construction, in this case, through the use of the match function. So you can see here that all this code works. I'm able to pass ints and floats and strings. I'm able to construct slices of duration and fruit and bill and use them as relating to the match function calls because we are defining there. Now you might say, Bill, you didn't define duration here. Let's run for a second. Let's guarantee that it works. Everything works. You might say, Bill, why is this working when duration isn't in the type list? It's working because Go can work off of the underlying type. The underlying type is int64. Int64 is represented, so it's there. Look, if I remove fruit from the list, we now have a problem. Fruit isn't in the list. But remember, fruit has an underlying type of string. So technically, I could even just say string here, and we are compliant again. It doesn't have to be just bound to fruit. If I want it only bound to fruit, then yes. I don't want the string, I want the fruit, then you have that. But if we really just want the underlying type represented, well, then we can do that as well. And as it relates to Bill, well, you know, that's a struct type. Hey, this doesn't work. Bill isn't represented as the list. Now it is. We need this as well anyway, because look, we have to be able to conform to the assignment. We have to make sure they're working with values that can be not assignment, equality, right? We can do that check. Okay. So this is showing you how we can leverage interfaces as part of the type list to define constraints to the data, both based on behavior and then based on what I would call a property of the data, that it is of some given type and or underlying type. Okay, any questions here? Not comments just yet, but questions here about what I've shown you. Okay, let me show you two more things. What time is it? 9:30. I know this takes a lot of time. I'm walking through the syntax fairly slowly so you can really comprehend it and then hopefully play with some of this stuff yourself. Let me show you at least two more things. The next one, I'm going to rush through. All I wanted to show you here with this example is that the type list can be of multiple types. So don't think like you're only bound to one type of, say, type T. We can define multiple types in the type list, in this case to be bound to, let's say, different parameters, in this case, two different collections, where I'm taking the value here and the value here and kind of merging them together. However, in this particular case, V must have behavior compliant to a string. And so V must have some sort of interface here, right? And I'm saying that V will be bound to the stringer interface so we can comply to the behavior. However, once a parameter in the type list is bound to a constraint, all have to be bound to a constraint. And so you might see this in some code where we're using the empty interface as a constraint to satisfy the compiler's syntax needs. Yet we're not really constraining L because anything can be of the empty interface type. So what you're seeing here is a type parameter list of more than one type, L and V, where V has to be constrained by behavior because of line 16. And now we must apply a constraint to L, and we're using the empty interface. All right, that's all I wanted to show you there, because you might run into some of that syntax, and now you understand it. Okay. Now I want to show you two kind of practical, well, at least one practical version of where I think generics wins out really well. I think one area where this draft, the support in this draft is going to add huge value in Go is anywhere where you're working with the empty interface today. There's some very, not a lot, but there are areas of the language where your only solution is the empty interface. Sometimes it's on a return type. Today in the context package, our value bag is empty interface based. In the sync package, we have pool and map types that are empty interface based. And the empty interface itself isn't the problem. The problem is that we now have to do type assertions to get back to the concrete data. And it would really be nice in all of those cases where if we could use the concrete type and remove the type assertion, the code could get cleaner. This also would be applied to data structures, like we wanted to write linked lists and queues and stacks. It also could apply to concurrency types of code, where maybe we want to have a generic implementation of a fan out or a fan in, where we don't have to do these type assertions from the empty interface. So I think this one area of the language where we can remove the empty interface is huge, and this draft really does take care of that. Now, let me show you quickly again here because of time. I wrote a function called retry. And the idea of the retry function, and this is stuff I have today in code, is to execute a function, and if it fails, retry it. And if it fails, retry it. And if it fails, retry it. And keep retrying it until you either time out or the function finally succeeds. Now, why would I ever need this? Well, let's say you're writing a service and you don't want to start accepting traffic until the database is ready. Readiness probes need this all the time. It could take a database 30 seconds to finally say, I'm ready to accept queries. And so this idea of readiness becomes important. And so look, I have some sort of worker function that's based on this type. I have an interval. I have a context for timeout. And what we do is we check to see if the context timed out. If it didn't, execute the function. Maybe this is doing a database query. If the database query is successful, then return the result back out. If it's not, and we haven't retried yet, instruct a timer, and then block here on the timeout or block here on the retry interval. If the retry interval fires, we execute the readiness function again. If it fails, we're back here. Do it again. If it succeeds, return. Eventually, the timeout should execute, and then we stop the timer, we return the error. So in this particular case, the worker function could be anything. Could be talking to different types of databases. Could be talking to servers that are out there. It could be anything. And so the result of this readiness function could be anything. So look at what I have to do in Go today. My worker function, my readiness function, well, it's going to return a value of some concrete type that we don't know about. So we use the empty interface, and we'll have to do type assertions on the other end. It's the same thing with the retry function. It's using the empty interface because this is the empty interface. So how much nicer would it be if we could define a worker function that doesn't return an empty interface, but returns a value of some type t that retry can also return? So it's clear that we're going to be working with the concrete data for any readiness function that we might implement over time. Here comes generics. Here again, generics is a fantastic way of getting rid of the empty interface. Now we say that our worker function, well, it returns a value of some type result. Notice I'm not using single letters anymore. When it comes to my collections, a value of some type T to be determined at compile time, a value of some type L, a value of some type V. But when we know the type has a specific purpose, like this is the result of the worker function, I find that it's more readable to specify what that type represents in the larger scheme of things. Using T here is not going to be as effective as saying, well, this type is going to represent the result. That's my opinion. This is something that we have to work on. I'd love your opinion on this as well when we're ready. Again, we're going to return a value of some type result, where the generic function is based on some value of result, where result will be determined at compile time at the call site. The rest of the code is the same. Hey, check to see if we've timed out. Call the worker function. But this time, we get to return the value as the concrete type itself. Or we, again, wait for a timeout, wait for a retry. Now, one other difference between this function and this one is the use of the return and the zero value. We know that the zero value for the empty interface is nil. And so you see me using, as we're taught, the literal zero value on the return for the errors, right? In this case for the, or when we're not going to return an error, we use the literal zero value for the error interface. In other words, we're using zero value on the return site where that's not what we're really returning. We want to continue that idiom in Go. And so we've got two choices when it's a generic function. We can construct a variable of type result set to its zero value using var, and then return 0 at the call site. This is what I'm doing here. Your other option is to use the new function to construct a value of type result set to its 0 value, getting back its address, and then dereferencing that. This is really what we have today in the spec for returning 0 value. We can construct that variable to the 0 value state, or you can do this. Now, some people like this. They think that it's more readable. I like this better. I think this is more readable. And some people like to just construct the 0 variable one time at the top of the function, and then use it at the call site. These are 3 options that we have today, and at some point over the next year, as a community, we're going to have to kind of agree to using one of them. I don't know which one just yet. This is something I want you to kind of think of and think about and consider. At this point, I like this. I like the construction of the variable close to the call site and using it, because I think it helps with readability, knowing where 0 came from. But I'm not completely adverse to constructing 0 one time at the top of the function and using it if that's the way the community ends up going. I think the dereferencing of the new function, that's a little too much. But some people like that. So here's an area where maybe we can still do a little bit of work. We've got to make some decisions. But what's beautiful is that the need for these type assertions go away. They go away because now we're working. Look at the worker function I wrote. It defines the concrete type that it wants to work with, not the empty interface. We get rid of the type assertions. We get to work with the concrete data directly. And I think there's big wins here when we can work with concrete types directly and not have to do these type assertions, I think. I think there's a big win there. All right, one last thing, and we're gonna open it up to some more questions and or discussions. I wanted to write a generic function that would give me some insights into what we could maybe expect from a standard library in terms of generic channels. So I wrote a function called doWork. What doWork does is it takes a worker function and executes that worker function in the scope of a Go routine. And when the worker function completes its work, it responds the result back over the channel. And so if you notice this function, it constructs a channel, returns that channel back to the caller, but it constructs the Go routine to do the work concurrently, in which case the caller now becomes the receiver. But we wanted to make this code work with any worker function that could return a value of some type, right? To be determined at compile time. So look at the type list again. We're defining that result is going to be a generic type to be determined at the call site. We're going to name it result because that's what we're going to be getting back on the channel, a result. And we define a work function to be a function that takes a context and returns a result of some concrete type. And so now I am defining a channel of some generic type result that the caller can listen on to get back the work. And if we were to just look at that code right now for a second, I construct a context of 100 millisecond timeout. I define a literal function where the result will be of type string. I return work complete. And then I block here as the caller, waiting for the doWork function to return or waiting for the timeout. So I've written a concurrent function called doWork that lets me time out that work if I want to. And so we're seeing maybe the beginnings of how we could leverage concurrency in the standard library with some really nice functions that we're all writing in one form or the other. I've also, it's a little more complex, tried to write a pool function. So the pool function has 2 parameters. We have an input, or the data that we're going to be posting in the pool, and a result. And so here again, you're seeing me define these generic types as an input and a result. You see here that the pool function takes a weight group, the size of the pool, and a work function to execute that takes some input and returns a result. You see me constructing a channel of some type input that goes back to the caller. And you see me creating a size number of Go routines that all listen or receive on the channel of some type input, passing that input to the work function, getting the result, and just displaying the result. And then on the call site, we can construct our work function. We can define a timer, how long we're going to wait. We can create a wait a weight group of that pool size. And literally I can now pass 10 pieces of work into the pool with a retry. And you can see here again, this is 10. And you can study this code a little bit more because it's a little more complex. That I'm writing functions now that are concurrent. You can see I passed 10 pieces of work into the pool. Some of them got done, some of them timed out. But it's all based on generics, right? Here the input is an int and the return is a string. Input, return types, all of that good stuff. And you can start to get a sense with this code in a more practical sense how we could have concurrent patterns in the standard library with some of the things that we do today. Okay, awesome. So I've spent this hour, maybe a little bit more, really trying hard to break down the syntax and giving you two kind of examples. One, we're able to reduce the use of the empty interface and therefore reduce the use of type assertions, work with concrete data directly. And another one where, and I went through it a little too fast because of time, where you could start to see how we could start leveraging channels and concurrency in a more generic way to where we don't have to write these patterns for ourselves anymore, but we can have these patterns exist for us where we just provide maybe functions that do the work and the rest of the mechanics are in place. And it's just going to make the entire Go ecosystem, I think, cleaner in terms of bugs, issues, and complexity. Okay, so with all of that being said, I'm going to open it up to questions, and then we're a fairly small group. So for those of you who have time, I really want to hear everybody's opinions. And then I would really appreciate as well that you fill out that Google survey and give your opinions as well to the Go team. If you want to spend some time playing with this first, then definitely delay the Google survey and play with some of this first. So the feedback you can give maybe can be a little bit more. And you can always fill out the survey multiple times too. It's anonymous, so don't hesitate to that. Okay, so Brian said he had to leave. I don't see anything there. Fast card question. If I already answered this already, so the letter T will be a kind of container defined by the compiler. Yeah, and that T could be anything you want as I showed you, right? It's an identifier, it's a name. So we as a community have to come in and try to figure out what's the best way to name these things so we know they're a generic type maybe versus something else. So I like the idea of single letters when it makes sense, but you saw me starting to use things like input and result. Some people complain that I'm using capital letters as if they're somehow exported and they're not. Using a lowercase letter has been tough for me, but these are the things that you need to experiment with. You have to practice with and start to get a sense of where you think it's best, and then we have to share that as a community. What's the advantage of using type T, stringer, slice T? Yeah, Vlad, that is a awesome question. It's a bit of a complicated question, but I'm going to do one thing since you asked it. I normally stay away from it. Let me share something here with you. Vlad, you see example number 9. Number 9 kind of answers your question a little bit.
Okay.
Now, the TLDR is that if I pass in T and use T for the slice, then the underlying type does also conform to the collection. So remember that I had named types like numbers, and numbers has an underlying type of int. Well, when we define things with just type T and a slice of T, then we can conform both to numbers and int because the underlying type gets to be compliant. But when you start doing things like, and if you look at this code here, I'm defining a constraint where the type has to be a slice of some type T. What we've just now done is taken the underlying type out of the equation. What we're now basically saying is S, in this case, has to be a slice of some type T, and therefore only numbers will be compliant. Not any slice of an int, but only numbers will be compliant. So when it's important that the slice itself is what you need to return or what has to be compliant, then yes, you need to bind yourself to that, say, one slice. But when the underlying type is okay, you want to do this. And honestly, most of the time, this is what you want to do. It's simpler. If you look at this syntax, right, I'm asking for a slice of some type T and then T here, and I'm saying that slice has to be of that slice, has to be S, but I needed the second type, in this case, for an operate function. It gets more complex. And so you can kind of see here, and I've commented out, that the compiler's doing a really nice job here on operate to identify that int is the base type. Now, I didn't put operate 2 here, but if I were to use operate 2 at the call site here, then only numbers would be compliant with operate 2, okay? But anything with int would deal with operate. Hopefully that explains it, all right? And hopefully that answers your question on why you would do one over the other. I think most of the time, the underlying type is what you really want to conform to, and it does simplify the code. But look at that example with a little more detail. I've got comments there, and we'll do a better job than I think I did explaining it out of the box. I don't get to explain that too much, so it's not refined. Yeah, I'm glad they got rid of the keyword contracts. I think it was confusing to have an interface and a contract. I knew I was having a hard time teaching it. But I do agree that having the type list inside the interface and now the interface not being used fully the way it can today could be a potential problem. So they're experimenting and looking at that. If you've got a nice, clean way of doing it, I think they're all ears. And I haven't seen anything from them on their experimentations. They're not sharing it with anybody. So I don't even know what direction they're going in yet. They're very careful before they share anything because there's an academic community out there just ready to beat them up. And what I'm doing, what I told them I'm trying to do with these meetups is reach the average developer who's not going to get into these academic fights, who don't really care about the academic fights, but do have thoughts and opinions that need to be opened and expressed. So that's really what I'm doing here. That's what the survey is about. But they have to be really, really careful before they show anything because you can understand the drama that it can create, and they just want to feel comfortable enough there. Someone with heavy OO. Yeah, so the biggest fear that everybody has in every meetup is that this is going to be abused and it's going to add extra complexity to everything that we do. And my answer to that is going to be is always the same, okay? We have to treat everybody like adults. And if somebody wants to add stupid, ridiculous complexity to their code bases, it's on them, it's not on us. And most people who come to Go for the first time in their first year abuse channels. Abuse them. I mean, I've seen the complexity of channels, and most developers who stay with Go after a year stop it. They realize the mess they made for themselves. So I think we're going to have some of that. I think people are going to abuse generics where they're not needed in their code bases, and a year from now they're going to go, what did I do? I think we have 10 years of experience with that type of abuse. So for anything that's open sourced, I think the community will use that opportunity to educate sooner rather than later. And I think the fact that you're asking the question means that you'll know, you better make sure after you have a concrete version Should we use our traditional polymorphic functions, or does generics here make sense when you need that decoupling? Everybody who's asking the question, I know will say that generics is an exception, not the rule. And that's kind of where we have to teach. Now, I will tell you this, Steve. I had generics in C++. I had generics in C#. I didn't use it because of the complexity. I don't plan to use it in Go. I plan the Go team to provide it in the sync packages, in the standard library where it's needed, where I would be using it, okay? But I want it not because I'm going to use it. I want it because there is an enterprise of software out there that can't be built in Go because it doesn't exist. And whether we like it or not, the banks, finance industry, those companies that really have to build for not that I want to be a part of it, but have to build these heavy frameworks because of their turnaround, because of their systems, because of that. They need it. They need some form of it. Now, I'm not sure if this first release of the draft gives them enough to build everything they need to. But it does give them a good start. And so if we see the banks and the larger enterprises come in and they start to be able to build what they have today in Go, it benefits everybody. Because it's just more Go being used in more places, more opportunity, more jobs, more work. And if I'm going to be selfish, I have a consulting company that helps these, especially these companies, with people and training. So even though I don't plan to use it on any given project, I mean, let's get real. Every language I've worked with, for me, has had basically a 20-year shelf life before next big languages come out. 20 years, you know, and Go is 10 years in. So if Go gets embedded in the enterprise like Java has for the next 10 years, there will be another language that comes out in 10 years that will start what Go did 10 years ago. There's no doubt in my mind. I hope to be retired by then. But if we want to see the same kind of growth that Java did, unfortunately, this needs to be in there. But at least we have a very pragmatic group of engineers doing it. And we'll do this over the next 3 or 4 years, maybe, before everything is in there. But I think we can educate well enough. But dude, I saw a code base last week where one of my students reached out saying, Bill, I told my team not to do that. I told them to do this. They basically told me to shut up. And I said, tell me what they're doing. Tell me what you did. And sure enough, they're writing Java in Go. That's their background. That's what they're comfortable with. That's how they're going to write code. It's not that they're going to fail, but they are adding extra complexities that we wouldn't necessarily want to see in Go. This developer now recognizes it, doesn't want to do it. And I said, it's all fair. You're going to have to write code like that for them until you get another job. And we'll see where that code base is in a year, because Go really isn't designed to do, you know, with everything we teach. But it's happening anyway. So, you know, the only way it stops is with you, Steve, making sure that your teams and your projects are being really careful. It stops with every individual. But the fact you're asking is beautiful. And yes, on every survey, probably half the people are worried about that. Okay, with all of that, does anybody have any questions? And then I want to open it up and hear some thoughts about everybody. So I'm just going to walk through the list and have a real hard time with everybody's name. Correct me when I don't say your name right, but I'm just going to walk through the list that I see here. So Steve, 1 to 2 minutes tops. I'd love to hear your thoughts or opinions or anything. Well, I got you here live.
Yeah, I'm really excited about generics in Go. I am, since I posted that question, I'm a little worried that there's going to be like a situation where a lot of unidiomatic stuff is going to make its way into the ether and people are going to pick up on it and run with it. Kind of like some early frameworks that were made in Go that are just kind of not really, they don't really feel like Go. So that That aside, though, I think I can definitely find a lot of places where I would use some of these generics. I don't necessarily see my workflow changing too much in terms of the day-to-day code that I write, but I do see some places where a lot of boilerplate can be reduced from using some of the things that you showed today. So I'm pretty excited.
Awesome. And one thing that I've done a couple of times, and I'll continue to remind the team, and it's on their list now. I told them that as it relates to generics, and though they've never done this in the past, they have to set this precedent. They need to document best practices. They need to provide a lot of code samples, and they need to define the design philosophies and guidelines that the rest of us who are teaching can sit on top of. I said, this is a time where it is critical that they do that before this is fully released. That way, nobody can have an argument about anything, because anytime the Go team says something, everybody just takes it as word. And it doesn't mean that we can't learn and change, but don't put this out there without it in this case, because that will help deal with some of the things that you said. Okay, Vlad, minute, 1 to 2 minutes. Questions, anything you want to feedback, concerns?
Yeah, that's gonna be a quick minute. So, well, basically, as I'm looking at it, I'm quite excited about it. Looks very interesting for me, something new, and I really have to dig more into it and find out if I like it and how much I like it. And if there are things I don't like, I'll reach out to someone, of course.
The survey is there for sure. Fill that out if you find things good or bad. Also, you can always send me an email, and then I can relay things, to Robert and Ian directly if I can't answer them or I think they're interesting ideas. I told them that most of us do not want to get into what I call sports talk radio on the mailing list and the issues. And so you can consider me like a backdoor to getting their attention and having a one-on-one conversation without it turning into what it turns into way too much. All right.
Okay, thank you.
Okay, Rabin, if I'm saying that right, if I'm not, please correct me. You have anything you want to share, add, questions?
Yeah, thank you for that amazing presentation. I loved it. And the reason I started using Go and loved Go was because of its simplicity. And Go is really simple. And the thing that I love most about Go is you can pick any package within minutes and understand how it is implemented and play around with it. That's something that has helped me while building products on Go. But as Steve has also told, I'm a little bit worried that people might misuse it and make that simplicity go away with the overuse of generics. But your answer was on spot on, and I've also felt like there was a situation when I was building products that I assume that if there was generics here, then the code will be much more cleaner and simpler. So I hope the future will be great, and I hope the community will not misuse this feature, this amazing feature. Yeah.
Brilliant. Okay, thanks. Again, this is good feedback as well for the survey. This current survey is open-ended, so you can really share these things. And I think the more that the Go team hears that, it will strengthen my arguments that they need to provide documentation here. Yep, I get it. Yeah, if you have to fall off. I'd love to hear from everybody, but you don't feel compelled. You have to share anything, but I'd like to hear your thoughts. So, Anita, if I'm saying that right, I'd love to hear your thoughts. If you want to share, if not, you can even just chat. No thanks.
Yeah, I haven't had a chance to work in depth in Golang, but the only concern or comment that I had in mind was about that data abstraction, like OOP, which is addressed. So yeah, I would need to do more hands-on before I can make any comments.
Okay, fair. Submit.
Hey Bill, thanks for your presentation. So I'm also feeling kind of similar with the people. looks like it's a compelling feature, and I was also thinking all the time where I could implement it in real. And I found a couple of places where I could, if we had a generic already, then it would have made my life easier. So I'm also looking forward to implement it in real and explore more. And till then, I feel it's a good feature one, and if people don't misuse or don't make it more complex by abstracting multiple things into it, it's cool.
Okay, awesome. Shankar, am I saying that? Shankar? I'm so bad with names.
Hello, Bill. Thank you for your presentation. It was a great one. So currently, when we are working on Go, so the problem we are facing right now is most of the code gets duplicated. So yeah, so looking at the previous language we used to work, so we used to have a dry principle. So I can see a lot of scope with this. So I really like this feature.
Okay, awesome, good. This next name is really hard. Somebody help me here. Pakzi? Oh man, this is horrible. Milad, how do I say?
Well, it's my real name is Milan. It's Tapagazi. Thanks
Okay.
for your insights. I was really wanted to talk to you in person back in 2019 in Go Meetup in India, but I could not make it sadly. But yeah, through this, I get to know about you because I've been following you through your tutorials, your blog posts. They're really nice, and yeah, you kept the same spirit. You explained it very well. I'm not like a real Go developer, but yeah, I'm a seasonal one. My background is mostly on system, but yeah, sometimes I poke around Go and yeah, build my simple utility tools. And yeah, Go is always my go-to language because of its simplicity and all this cool stuffs. Yeah, I don't have much thing about the generics, but yeah, I was curious to know what really happens when we have when we use these type informal stuffs behind the scene. If you have any time, like, can you explain a little bit more, like what goes in behind the scene, like you do in your tutorials?
I can't do that right now, but I'll give you my email address, and you can send me an email with that, and I'll do my best to
Okay.
share what I can.
Yeah. Thanks,
All
Bill.
right, got it. Bishnu, if I'm saying that right.
Thanks, Bill. I had to listen you. I had to attend your presentation. That's why I'm here. But I'm really not into Go yet. But looking into your presentation, having option in your toolchain, it seems to be promising. Thank you, Bill.
Awesome. Rohit. If you don't have anything that's fair, probably not. All right, W. I got W here. You want to share anything? Michael, want to share anything?
Hey Bill, yeah, sorry I got in late into the presentation, so missed out most of it. But yeah, I think as you're saying, the interesting one will be where examples of where we can use it correctly. So one thought I had was like, if let's say you're parsing through, let's say XML, where the form is not really well defined, is that like a good case where you're using generics? And another question would be, testing wise, would it be easier or more difficult with generics in it?
Reflection is still a really powerful tool. So if you're doing marshalling and unmarshalling, I still think you're going to be using reflection there. I think for this current version of the draft, I believe the real focus is on anywhere you're using the empty interface outside of maybe reflection, because that, you know, I don't think you're gonna hand code a bunch of different types for marshalling and unmarshalling. So they're no good. And the collection kind of types, I think that's where the big win is there. But I want everybody to kind of use it as an exception, not a rule, right? But those are good questions. And the best thing to do is experiment. You know, write something today, hard code it, try to write a generic version with reflection, and then try to use your generics and just get a feel for it. If you don't prototype, you won't know. Okay, who do I got left? It hasn't. Oscar, have you expressed any opinions yet?
Not yet. Thank you, Bill. It was great talk. Yeah, regarding generics, it was kind of a talk of a town, and I really wanted to know how the team would implement generics in Go. Yeah, but yeah, this is really amazing how it is designed by the team, and yeah, it looks promising. I've never thought of using generics while working in Go, but yeah, after your talk, I'll give it a go and fill the form, survey form. Yeah, it's really inspiring. Thank you for the talk.
So Milap, I got the links there again. Maybe you can send those to everybody on Meetup one last time to get the Google survey going. Did I ask you, did you, I don't remember if you gave any opinion.
No, no, not
yeah,
yet.
so share yours.
Yeah, sure. So I tried using on the playground, the new playground for the generics, but I tried very basic things there. And from today's presentation, I learned a little bit more about it. So how from using from channels to everything else. So I'll give it a try on those stuffs as well, and fill up that form as well, I guess. So I think like misusing is something that could be done with interfaces as well and everything. So so I'm really excited for having generics. And like it helps solve some kind of problems that only interfaces we were trying to solve with interface previously. So so yeah, excited and looking forward to it.
Awesome, awesome. Hey, if you ever come up with some interesting examples that you had this aha moment about, like if you write some code and you had a light bulb turn on, can you send that to me? Because I'd be interested in seeing it. Maybe
Yeah.
it's stuff I should have here in the repo. So, and that goes for anybody, you know. It's those aha moments that are important, because if you had one of those, somebody else will too.
Sure.
Okay, brilliant. All right, so that's all I got. Great feedback. We'll publish these links again on the meetup, and then I hope everybody gives the Go team a little feedback here and there. Other than that, have a great evening, everyone. Thank you for letting me be here.
Thank you, Bill.
And I don't disappear. You got my email address. Send me an email, and I'll be as quick as I can to respond.
Thank you, Bill. Have a good day ahead.
Thank you. Thank you, everyone.
Ciao.
All right, Mark.
Bye.